All right, hello everyone. Welcome back to week 6 of Intro2Astro 2022. Thank you so much for joining us today. This week, we will talk about the process of grad school application, and we'll hear from our special guest, Caitlin, who works for NASA, by the way. Caitlin will tell us about ongoing exciting research in planetary science, particularly Pluto. Finally, Shu, who is about to start grad school in a few weeks, has kindly agreed to share with us his life story. Again, if you have any questions, please feel free to post them here on YouTube or on piazza.com. All right, without further ado, let's move on to the first topic today, grad school application. And the speaker is Jack. The floor is yours, Jack.
All right, thank you. We're going to talk about grad school, the application process, what it's like, what you're going to need. We're going to talk about some deadlines that are imposed by schools and some deadlines that maybe you want to self-impose on yourself. And ultimately, I think though it's important to remember that, just like any kind of application process, it's definitely going to be a long process. It's going to require a lot of your time, and that can be tough to balance with all the other responsibilities we have going on in our lives. Also that something to keep in mind is that if at the end of that process and you have applied, if for whatever reason acceptances don't come in your way, that is not in any way a negative reflection on you. This process is intensely competitive, and it's only gotten more competitive in the past 5-10 years. And I know many people who have applied one round, not gotten in, they apply the next round and they get in to great schools, and they go on and have very successful graduate careers and beyond. I know people who have applied and not gotten in 2 rounds in a row and gotten in on that 3rd round. So do not get discouraged if that first time around things don't quite go your way. There's still many ways to stay involved in astro and ways to kind of bolster your resume, if you will, or your CV, like we talked about last week, for then that next round. You can always be improving. And if you stick to it, I'm very confident that it will come your way. But so with that, I got a little bit of a slideshow here for you about applying to graduate school. And so we'll step through some of this. Let me get my Zoom screens out of the way. Okay. So kind of just a general overview of things that you're going to need to apply to grad school. Each school that you apply to is going to have its own application. There's no like common app for graduate schools like there is for undergraduate schools, at least in the United States. So you're going to have to enter your information in as many times as you're trying to apply to schools. There also are application fees. Those can really add up. Applying to school can be expensive. However, like we'll see that a lot of places offer fee waivers. We're going to talk about that a little bit. Next, you're going to need what they call a personal statement. It's an essay about who you are and what you've done and why you want to come to grad school. And this is really a chance to kind of show yourself off to the admissions committee of the school. Next, you might need standardized test scores. We're going to talk much more about that later. So I've got 2 asterisks next to it. You're also going to need minimum 3 letters of recommendation. All places require 3. Some will allow you a 4th, but all require 3. Then we're going to talk about transcripts towards the end, and we'll wrap it out with some other as well. But now I want to give just kind of a general timeline of things to be thinking about when you're beginning to apply to school. And I know this is a lot of text on the page, but I want to make sure I got it all on there and didn't forget any. The most important thing is that you should really start early. And I really mean early, because most schools have deadlines either December 1st or December 15th. And by the way, I'm talking specifically for physics and astro programs, by the way, but a lot of this applies to other STEM graduate programs as well. So at least in physics and astro, a lot of schools have December 1 or December 15 deadlines. And so that means you might even want to start this process now. Now being the date of this recording is July 18th. So you should really be starting to consider a lot of these things even as early as now, 6 months ahead, because it'll really help you in the long run if you do. One thing that you'll want to do fairly immediately is get your transcripts in order. You can get that from your school. They can be unofficial, as we'll talk about later, but that's something you want to do early because you don't want to be waiting on your school at the last minute to try to send you a transcript so that you can upload it to some website, and you don't want to be dependent on anyone else. You want to have all those in hand. When you get some free time, you want to be filling out these applications, just plugging in all your personal information because you're going to have to do it. If you apply to 10 schools, you're going to have to do it 10 times. And this can be really tedious and annoying. So I recommend watching TV or something and just doing it while you have that in the background. But do that early because, again, you don't want to be on that last night on, December 14th, and you got to upload all your personal information and it's a huge hassle, and, you're racing against the clock. You don't want to do that. Next, if you do have to take tests, the standardized tests, you want to take them as soon as you can, or at least you want to start studying as soon as you can so that you can take them with enough time to give yourself perhaps a second try if you do want that. But again, we're going to talk more about tests later. I have a lot of thoughts on tests. Next, you're going to want to start thinking about your personal statement, even as early as now in July. Certainly into September and October, you want to be writing that personal statement so that you have time to give it to others to get feedback. And lastly, and this one's really maybe the most time dependent, is you want to ask for these letters of recommendation really early. I've given a kind of rule of thumb here of 10 weeks before the deadline, and that would roughly be October 1st. But earlier is better. You're more likely to get people to agree to write letters if you ask early, and you're more likely to get better letters if you ask early, and they will be much happier with you if you ask them early. So just generally, asking 4 months in advance is not unheard of. Don't feel like you're going too early. They would probably even thank you. But anyway, we'll talk more about that later. Just again, some general advice, starting early is important, but also organization is going to be key. You're going to have a lot of balls juggling in the air, and you don't want to lose track of any of them. It's going to be very easy to lose track of them. And so, for example, when I applied, I was keeping spreadsheets of things that I had done and the things that I had yet to do. Just making checklists. Each day I had a couple items I wanted to get done. So organization is really going to be key through all this, especially if you're applying to a lot of schools, of which today people do tend to apply to quite a few. We'll talk more about that towards the end, though. And again, I just want to reiterate that first time around, if you're not accepted, that's not a the end of the line for you. I again know many people who've applied multiple times and eventually it works out for them. And so do not get discouraged if it doesn't quite happen the first time. So now more into those individual items that you're going to need, the actual application. Again, there is no common app, so you're going to have to do each one individually. There is an application fee for every place you go. And they have a wide range of costs. I was looking at a couple. I've seen as low as 60. I've seen as high as 150. And actually, sometimes it's even higher for international students. And I say international in the sense of outside of the United States, or students coming from outside the United States, I should say. So one thing that's really important is that all schools also offer fee waivers. Not everyone knows this. A fee waiver literally just means they waive the fee. There is no cost to you. The department or the school will decide that you don't have to pay the fee. There are a lot of different rules about who can get a fee waiver and why you might be eligible for a fee waiver. All schools will post that information on their website. Generally, these are policies that are set by the school as opposed to the department that you're applying to. And so the rules might seem very rigid, but I highly encourage you to contact the department that you're interested in joining. If it's the physics department or the chemistry department, whatever it might be, or the astro department in our case, try contacting them to ask about fee waivers and explaining your position and why you might need or want help on these fee waivers. A lot of times the departments have a bit more wiggle room than the actual schools themselves. So I highly recommend that you contact these departments if cost is prohibitive to you, because I know a lot of departments don't want cost to be the prohibiting factor to applying to their department. And so they will help you if they can. But again, I would highly recommend actually contacting them. Next is this essay. Some schools have multiple essays. but every school has at least one. They call it the personal statement. I've thrown up a link here to some advice that I saw online. I thought this was a really good website with advice on how to actually write your personal statement, because I myself don't remember necessarily everything that goes into it, and it's certainly kind of changed over the last few years, particularly with COVID, things that you might want to include. So I recommend you kind of browse this website, but there's many sites like this that give advice on how to write your personal statement. But generally, the personal statement is just it's supposed to be your way of introducing yourself to the admission committee, telling them who you are and what you've done in the past, what you want to do in the future, why you want to go to grad school in the first place, and what you hope to get out of it. Nothing that you say in this essay is ever binding. I mean, you could say you want to study XYZ because then you want to go work for some company XYZ, whatever, and then later you decide, oh, actually, I want to stay in academia and teach. No one will ever hold you to anything you say in this essay. Something that I think is important is, and this is part of starting early, is that you want to have a full draft of this personal statement early enough that you can then give it to others so that they can read and give you feedback. People that might give you feedback are the first three people I would ask are my three letter writers. Hey, will you also give this a quick read and give me some feedback on it? You could ask parents, you could ask friends, you could ask grad students who are already in school. You could ask professors that you've worked with in the past. Feel free to reach out to these people, because I mean, the worst thing they can say is, no, I don't have the time to read it. But if they do read it, they can probably give you some really good advice. That said, if you do give it to a lot of people, you're going to get a lot of advice. And some of it's going to be great advice. A lot of it's going to be good advice. Some of it's going to be bad advice. A lot of it is going to be contradictory advice. Don't feel like you have to take all of it. It's still your essay. It's your personal statement. So don't let too many cooks in the kitchen, rip apart your statement. It's still yours. In the bottom here, I've included just kind of they're calling it a classic application prompt. I took this right off that website that I've linked above. This is generally what these prompts look like, these personal statement prompts. They say, why are you interested in school? Why do you want our department? And then talk about your areas of interest and future career plans. This is what a general prompt looks like. Next, we get into the topic of standardized tests. Now, historically, there are these two tests, the general GRE and the physics GRE. The general GRE is 3 sections or 3 topics. It's like language comprehension, I think it is. It's like reading paragraphs and then answering questions about the content of those paragraphs, and a lot of things on like word choice and definitions. Then there is a math section, which is usually algebra and geometry, some statistics, things like that. And then there's also an essay section. That's the general GRE. Then there's the physics GRE, which is I believe it's 100 questions, multiple choice questions. You fill in the bubble, and they're entirely physics topics. They're a whole range of physics topics. They're really the questions are supposed to span the entirety of like an undergraduate education in physics. My personal opinion, both of these tests are not good tests. They have a lot of biases to them. They are gatekeepers in many ways. They're very expensive. They cost hundreds of dollars just to take. They cost even more if you want to buy the books and potential tutoring to go with those books. This is a very expensive endeavor. And so it's not very open to everyone, quite frankly. And a lot of people in the field, astronomy, physics, recognize this and are starting to take the steps to no longer require or even not accept these test scores. And so I urge you to when you do have a list of schools that you are interested in applying to, make sure you check out if these test scores are not required or not accepted. There is a difference. Not required meaning you can submit them if you want. Not accepted means do not even submit them. We don't want them. Personally, I hope in the next year, 2 years, I hope in the very near future, all schools move to a not accepted policy. I don't know if that's imminent, but I certainly hope it's moving that way. I know, for example, my school, University of California, Irvine, we have moved to a not accepted phase. So do not even send us both tests, by the way. Don't send us the general, don't send us the physics. They don't want to see it. Some schools are not accepting the general, but are still requiring the physics. So these, you might have one or the other accepted or not. These are things that you should really check out when you're applying or choosing schools to apply to. In particular, because the general GRE, you can take, I think, almost any day of the year. You just kind of sign up, and there are testing locations all around the country or even world. You can just go take these tests. I think you can even take it online now. The physics GRE is only offered twice a year. One in like September, I think, and one in October or November. So if you don't sign up for those 2 exams out of the year, you miss them. And so then if you needed a score to apply to a school, then you don't have them. That's another reason why I hate the physics GRE. I don't even think it really tests very well, like physics understanding. I mean, it's just really a bad test. And I'm very thankful that a lot of places are not requiring it anymore or not accepting it. And so all this said, I personally know people who have specifically not applied to schools that require one or both of these tests. And I would urge you to consider that as well, if this is something that you don't want to do or can't afford to do or don't have the effort and time to do. The field is moving towards not requiring them, and some places are being stubborn and holding out. And so in some ways, we could use like the power of the people. If many people don't apply to these schools, then maybe they'll get the hint and drop these requirements. So something to consider. Now, if one of the schools that you really want to go to for a variety of reasons does require them, then maybe that's worth taking them. But it is worth investigating or thinking about to yourself, is it worth pursuing these tests? And how much am I going to get out of taking them and applying to the schools that require them? So that's a thought on standardized tests. Next are the letters of recommendation. So again, every school requires 3 letters. Some schools will allow you to submit a 4th, but all require 3. And this is something that you really, really, really want to start early, because these professors and even postdocs, they are so busy. They write a lot of letters for a lot of people, and it's really a very taxing kind of job to do. But in many ways, it's like the one thing that they can give back to us. We give them, if you worked for someone in your undergrad, you've given them a lot of your time and effort to do research for them. Kind of the one thing that they can give back to you is a letter of recommendation. So don't ever feel like you can't ask for a letter. In some ways, it's the unfortunate currency of academia, or these letters of recommendation. And that in itself is a whole bad system, but we don't have time to get into that. The idea is that you ask these 3 people. They most often are people you've done research with or people you've taken a class from. Perhaps it's your undergrad advisor that you didn't necessarily do research with, but they just know you really well. If you have worked in an internship or just in an industry job, they can be your manager, they can be your coworker, they can be anyone in that space. They can be people you've done science outreach with. Maybe you've been going to your local museum for a year or 2 and given little lectures on constellations. It could be the museum curator. These can be a wide range of people, but you do want them to know you fairly well. You don't want them to write a letter about someone that they don't know. And so the other thing, though, is that it's okay to ask different people for different reasons, or to ask them to focus on different aspects of you. You might have an advisor that you did research with, and they'll know you really well from a research and work perspective. Then you might just you might ask a professor who you took their class and you just really enjoyed it. You didn't do research with them, but you enjoyed the class, you enjoyed them, and they, you went to office hours a lot and they know you. Feel free to ask them to give more of like a general background of who you are as a student as opposed to who you are as a researcher. And so different letter writers can focus on different parts of who you are and different parts of your story also. And again, because they're so busy, it is okay to, I put in quotes, to bother them. Make sure you're reminding them that these deadlines are coming up. Make sure that you make this as easy as possible on them by providing them with all the links that they need to actually upload these letters to the various applications, make sure they know their deadlines, make sure they know if there are page limits, if there's margin limits. I can't think of it if there were, but make it as easy as you can for them, because while they are doing you a favor, you maybe have done favors for them as well. And so it is, it's a two-way street, but it is hard on them. So if you can make it easier on them, that's always a good thing. One of the last things are about transcripts. All places will require transcripts. However, almost always unofficial transcripts are okay. And then later they would ask you for an official transcript upon an acceptance. Like I said earlier, get these from your school ASAP, because sometimes it takes processing time and you don't want that to be the holdup when you're trying to hit submit on the night before. So get these early. They're just PDFs. You can save them on your laptop, and then you have them for when you need them. And then just some kind of last things are that, again, each school has their own requirements. So when you've decided to apply to a school, read them all, read the requirements very carefully and know what you need and what you don't need. Some schools will ask for an interview. I was interviewed once and then I didn't get in, but they will ask for an interview perhaps. Don't be intimidated by these. They mostly just want to kind of talk to you, get to know you, kind of get a little more information out of you than what would be possible from just the essay alone. So this sometimes happens. And then lastly, again, talk to people who've done it. Talk to people who've gone through this process, who are in grad school. Talk to people who are professors now, who are on the admissions side. These are all good people to talk to. And then I am running out of time though, but I do want to mention just a little bit on like how to choose a school or how to choose a list of schools to apply to. And the first thing I would say is ignore this concept of like the prestige of a school. There are schools that are considered, quote unquote, better than others or more prestigious than others. Forget all of that, because when you're applying to graduate school to do research, cutting edge research, it's so much more important to choose a school based on what kind of research they're doing and what professors are there doing that research. So take the time to really look at a wide range of schools and think about what topics you might be interested in, and then find which professors there are doing that kind of research. You can be thinking about, hey, if I were to go to this school, who would I want to work for? Who would I want to be my advisor? Because I find their research really interesting. And then consider applying to that school. Because you might find that you're really interested in some topic, and then you look at the website for some of these, quote unquote, prestigious schools, they might not be doing that research. They might not have anyone actively pursuing that area. And so then if you were to go there, you're not going to be learning the things that you want to learn, regardless of what the name of the school is. So it's really important to actually kind of work through these websites and figure out what kind of research is actually happening at these schools. And then it also could be really beneficial to reach out to one or two of those professors that you find at each school, and just introduce yourself. Hey, I'm applying. I've done this in the past, but I want to do this in the future. I recognize that you're doing this kind of research. Can you tell me more about it? Just kind of open up with a question to get them to talk to you a little bit. I know professors love responding to these kind of things. I also know that they get a lot of emails and sometimes lose your email in their inbox. So it's totally okay to send them a follow-up or a reminder, a week or so later, give them some time to get back to you. But if you haven't heard back, feel free to kind of poke them again and say, hey, just following up on this email. I wonder if you get a chance to read it. But what that can do is it gets your name into the mind of someone already at the school. They might be on the admissions committee. They might be talking to people on the admissions committee. They might help you get a fee waiver if possible. So reaching out to professors, individual professors at schools, just to learn more about the program and about the research that they do in particular can really, really help you in the long run. And then, of course, there might be other factors for which you might choose to apply or not to apply to a school. It might be just physically, where is the school? Might be a really important thing. I know it was for me, and so it very well could be for you. So anyway, this is general kind of information on how to apply to schools, to grad schools. There's a lot of information there. So if you do have questions, please do write in the comments or in Piazza, and we'll try to get back to you if we can, as soon as we can. But so thanks. I'll turn it back to Faye now. And
thank you so much, Jack. It was a lot of useful information. I wish I knew this when I was undergrad. Thanks a lot. All right, our next speaker is Caitlin. Before you start, Caitlin, could you briefly introduce yourself?
Sure. So, hi everyone. I'm Dr. Caitlin Ahrens. I'm a postdoctoral researcher at NASA Goddard Space Flight Center here in Greenbelt, Maryland. So, hello from the East Coast. So, my STEM journey I'll talk about a little bit here later, though. But being a postdoctoral researcher means that I already have my PhD, and now I'm just working my way through on my way step toward becoming either a government civil servant or academics or industry. So a postdoctoral researcher means just kind of getting your footing in whatever line of work that you would want to do for usually about 2 to 3 years. It's supposed to be a very short time. But it gets you to just do more experience, more research, and it's a fun experience from there. But I want to, hands to Jack for all that amazing grad school application advice, though, because that is very, very important. And I agree, Faye. I wish I had known some of that when I was an undergrad.
Yeah, definitely. All right, feel free to start. The floor is yours.
All right. So before I share my screen, though, so I am a planetary geologist, but my degrees are astrophysics and geology. So hooray, you combine the two and you get some really fun stuff with planetary science. But the interesting, really cool thing about planetary science is that we're a very interdisciplinary community. There's a lot of folks that only did an astrophysics track. There are a lot of geologists that maybe have never taken a physics class. We have chemists, we have biologists, we have pre-med students as well for astronaut studies. We have aeronautical folks. So all of this is very, very interdisciplinary, and I'm happy to answer questions about planetary science later on. But tonight, I'm going to talk about just one little tiny aspect of planetary science that tends to get kind of ignored, and this is experimental planetary science. So what I mean by planetary experimental science, though, I truly mean recreating planets in a laboratory. How awesome does that sound? It's incredibly difficult, though, to say the least. But real quick, my little STEM journey here, like I said, I have a physics, astrophysics, and geology degrees from West Virginia University. Through my undergrad years, I was kind of hopping around all over the place. I did radio astronomy for a number of years. I was doing pulsars. I'm also a seismologist by trade as well. I did rocket payload systems and Mars. And that was my first true taste of planetary science. I just happened to do a quick summer project on Mars and didn't even know planetary science was even a career choice until I was doing Mars work, and I'm like, this is where I'm gonna have the most fun. Let's do Mars. I landed at the University of Arkansas doing my PhD in planetary sciences, doing Pluto. So switching from Mars and then all the way out to Pluto was a bit of a turnaround point, but it was great. I got to run my own lab, and I will show you pictures of what my lab actually looked like, and did a lot of geologic modeling of Pluto. And so, like I said, now I'm here at NASA Goddard Space Flight Center on the moon. So I went from Mars to Pluto, and now I'm back to the inner solar system with the moon. And I'm part of the Lunar Reconnaissance Orbiter team, science team. So lots of fun stuff there. But like I said before, planetary geology, just so many different aspects. So planetary geology in general, we have thermodynamics, which is what I mostly work on, rheology, morphology. So the bending of materials, the volatiles or the gases, the liquids, the solids, how do they all interact? How do they all solidify or sublimate or liquefy? Geophysics, so big scale, how do mountains form on other planets without plate tectonics? How do volcanism work from the interior mantles and core systems all the way out to the surfaces. So all of this needs to be all jumbled together and communicated for planetary geology, and it's really quite fascinating. If you're more on the astrophysics side, astrophysics is more of the outside of planets, but that's still very important. We have to chat with a lot of heliophysics people. Me specifically, I work on ice, but a lot of that ice in the outer solar system is heavily irradiated. So I have to talk to heliophysics folks and go, hey, what is the sun doing? What's the chemistry of the sun and the solar wind and plasma doing to my ice? So it can get really entertaining. And it's truly not just one type of ice. There are so many different types of ice to keep track of too, and different kinds of metals and different kinds of silicates. So it all depends upon what part of the solar system that you would want to do for your experiments, for the sake of this presentation. So if you want to recreate, say, Mercury or Venus, you're obviously not going to really care about water in any sense of the word, or ice. But if you're wanting to do, say, Titan, at Saturn, Titan gets down to 90 Kelvin temperatures. So that's negative 300 some degrees Fahrenheit. Very, very cold. Your water ice will be completely solid. What other kind of ices would you need from then on out? And then the farther out you go, the more stuff freezes from then on out. And water ice can get very complicated too. So there are 19 crystalline types of just water ice, just pure, simple H2O. But this gets really entertaining though, because it all depends upon your temperature and pressure. So we kind of tease it around saying 19 crystalline types could also be 19 different yoga poses of water ice. It's truly just your 2 hydrogen and oxygen. How complicated can you be? But it really does depend upon your temperature and pressure, and then it depends upon how well does your structure fluctuate. So we deal with temperature pressure diagrams like this, figuring out what are the different crystalline types of water ice under what temperatures and pressures. For ocean worlds, so when I mean ocean worlds, I mean very solid ice crust moons of Jupiter, Saturn, and beyond. But the interiors of these moons could either have had some sort of salty ocean or currently having some sort of salty ocean going on. So understanding those oceans, very high pressure, higher temperature water ice versus the surface, which is very low pressure, very, very colder temperatures from there on. So like I mentioned before, it's truly not just water ice either. We have to keep track of all of these different kinds of ices as well. So carbon dioxide, methane is a really fun one to deal with. Ethane, carbon monoxide, my personal favorite, nitrogen. So all of these to deal with a laboratory with experiments. And most of these are very, very dangerous to handle in a laboratory, especially ethane and carbon monoxide. If you're wanting to do like Titan experiments, you're dealing with way more dangerous chemicals from there. If you're dealing with a Venus, you're not dealing with ice. I'm specifically working on ice, but if you want to do a Venus experiment, you're dealing with very extreme temperatures and pressures. And I'll show you a picture of a Venus simulation chamber here in a bit. But lab work is incredibly messy. The key is to be very, very organized in whatever you end up doing if you decide to kind of get your hands dirty. There's a lot of wires and there's a lot of chemicals. And there's a lot of lab training, and every university that has some sort of lab setting would have you go through lab safety training multiple times through your years as a grad student. So very important to go through those kinds of training. Yes, it can be boring. Most of it's just watching YouTube videos of don't hurt yourself. But needless to say, there's a lot going on in your laboratory, and to really understand what you're wanting to do kind of deal. But very, very fun nonetheless. But why do lab work? What's the importance of doing planetary laboratory work? Well, it's interesting is that you have in planetary science the perfect trifecta here. You've got your missions, getting data at whatever planet and moon that you're out at, whether it's ground-based telescopes or maybe a flyby like New Horizons or orbiter mission data. You have all this data. What are you going to do with it? Now, most of the time you can just go straight to modeling it, going like, oh, well, we got all this data. Let's see if we can model it and recreate it. What does this data kind of tell us about such and such surface or oceans, or maybe the magnetosphere or the plasma environment of something, or the atmosphere or interactions. But modeling can only take you so far. And so modeling parameters and how you interpret the data still stems from experimental data as well. Like I said, we have 19 crystalline types of water ice, but most of that, if anything, has come from experimental data. Or understanding how ice works at 10K temperatures all the way out to Pluto. We don't have anywhere at 10K temperatures here on Earth at a natural environment. That would be really interesting, but really, really cold and thermodynamically impossible at that point. But regardless, having any kind of analog here on Earth of those kind of cold temperatures is there's nothing around. So you got to do experimental work and understand like, oh, these are the physical properties, the thermodynamical physical properties of these kinds of ices or metals or gases, volatiles, anything at those temperatures and pressure conditions. And then that can help you with the modeling, that can help you understand what all the data that you just got. So experimental is part of this trifecta here. So a good example here is we got beautiful spectroscopy data, chemical data from the New Horizons flyby. So when I mean flyby, I mean New Horizons didn't stop at Pluto. It truly approached Pluto, got to Pluto in July 2015, took as much data as it possibly can, and just kept going. Hence the name flyby. But while it was at least zooming past, it was able to get a lot of really nice chemistry data on this part of Pluto, which we found where are the good concentrations of nitrogen, methane, and carbon monoxide. Great, we have data, now what? From these concentrations, we're realizing that there's different kinds of geology. There's maybe glaciers where there's more carbon monoxide. We're seeing sublimation pitting. Where there's more nitrogen, we're seeing some really cool mountain features where there's methane. What would this all mean? And so this is a snapshot picture of the lab I ran and built back at the University of Arkansas. So it was myself and an engineering student. We took about a year and a half out of truly just starting on a tablet, a piece of paper tablet of what the design is going to be, to making it run. So it took quite a bit of time, but you know what? On a shoestring budget, not too bad. But this Pluto simulation chamber can get down to 10K temperatures. The hottest it will go is 60K temperatures. So you're going from cold to colder at that point. We didn't do anything with water ice because water ice is a pain to deal with. So we just stuck with nitrogen, methane, and carbon monoxide. So similar to the three main chemistries that we saw at Pluto. And we did mixtures. We did different kinds of ice mixtures, different kind of ratios of the mixtures, pure ices as well. And the little probe that you see here, let me get a laser pointer here. So the probe that you see here, you can see the ice, you know, just very fancy icicles at that point. But the probe here would shine a light, and that diffusion of light will go back into a sensor, into a laser sensor. This is what's called FTIR, Fourier transform infrared radiation. So looking at all the squiggles, very, very fancy squiggles at that point. So the laser will read whatever is being diffused off of that ice, and it will give us a spectrum. And then you can get more and more spectra. When you crank up the temperature, maybe you would play around with your pressure, and you would get the different kinds of squiggly lines here. But every single squiggle that you see here is very important. It tells us a story. Every single piece of ice in the world of chemistry is like a fingerprint. And so a very famous one are the three pointy ones here and also over here as well. That is methane. As soon as you get the three main points in that part, usually between 1.7 to 1.8 microns here, you know that you have methane. As soon as you see those, you have methane. Everything else, it really depends upon what you're mixing. Methane is very, very noisy, though. I will tell you that. So in that case, though, again, why do planetary experiments? It's truly not just for the benefit of modeling. We want to know what's the property of these materials. We want to understand what's the origins and evolutions of these materials. If your nitrogen and carbon monoxide is solid up to a certain temperature or pressure, and then it changes or sublimates or whatnot, your phase changes happens, what can that tell us about the different surfaces of these planets and moons? That could all tie into the chemistry, the physics, and even astrobiology as well. There's some astrobiology at Mars. There could be some astrobiology at Venus. There could be astrobiology in the oceans at Europa and Enceladus. So understanding all the material properties, the ice, the salt, the silicates, the metals. And also risk assessments for instruments. If we say we want to put a drill at Titan or eventually at Europa, we really need to know how solid this ice can be, so that way we don't destroy the one drill you're going to send to that moon. Let's see here. So just some very basic questions that we consistently ask ourselves as to, like, again, why do we do experiments versus using ground-based observations like telescopes or modeling. So say if we want to know the composition and structure of, say, Pluto, okay, we have ground-based spectroscopy. We can get temperature data, maybe barely geologic mapping, at least from flyby observations. Okay, that could tie into modeling with like geophysical evolution, looking backward in time, looking forward in time. But experimental, again, you really get the thermodynamics, the phase changes of the ices. Same thing for maybe power sources, the interior heartbeat of these moons and planets. You can't obviously just get a stethoscope out to the moon or planet and listen for it or anything. So ground-based or even flyby observations, okay, you can get orbital properties, maybe a little bit of tidal interactions, modeling tidal evolution, maybe convection modeling, but it still comes down to material properties from experimental stuff. So other kinds of configurations, you don't need a big, fancy, shiny chamber. You could also have very small chambers as well, or even what's called sample cells. So the scale of this is really quite small. It could fit on a small table, but it depends upon what all you want to do. So like Raman spectroscopy versus the FTIR, it can give you different senses of the chemistry and the atomic structure of your sample. This one's a really, really big chamber, though. This is at NASA Glenn out in Ohio. This is the Glenn Extreme Environments Rig, or GEAR. So GEAR is gearing up for some Venus high temperature, high pressure experiments coming up. So it's going to get really busy coming up very soon. It's going to run a lot of rock samples. It's going to melt a bunch of stuff. It's going to be great. It's doing Venus, but there's plans, I believe, to also do some like hot exoplanet research as well. Here at NASA Goddard, there are a handful of Venus hot environments chambers as well, so much smaller than the GEAR chamber, but it can still do high temperature, high pressure experiments, just different instruments. It can tell us different things about the different properties of the materials. Open University out of the UK has a beautiful big Mars chamber. They mostly do a lot of regolith studies, which means a lot of dirt and soil studies, somewhat of ice, carbon dioxide ice as well. There's quite a bit of carbon dioxide ice on Mars. So they try to mix and layer a lot of that ice and dirt together and do some really cool experiments with that. The University of Arkansas also has a Titan chamber. This thing is massive, but it can get down to Titan temperatures and pressures. So the pressure of Titan is about 1.5 bar. So not so bad. It's not low pressure at all, but temperature-wise, gets down to 90 K temperatures, so pretty cold. But very, very interesting chemistry on Titan. The Northern Arizona University is very exquisite for their planetary experiments, though. So if you're really interested in doing planetary experiments, look into Northern Arizona University. Very, very fantastic university for this. So they have much smaller instruments, but they have way more complex ways to study material science from there. But if you are interested in low temperature material science or thermodynamics at low temperatures, the newest textbook of the Pluto system after New Horizons came out just last year, I believe, or sometime, I don't remember. Yeah, 2021. And I myself have helped my two co-authors here on many, many pages on experiments from the 1920s to present of low temperature experiments. And turns out there's a lot missing. There's still a lot to be done, which is really good. But 1920s to present, not a lot of experiments actually happen. So yeah, just real quick though, so Titan is a really fantastic moon of Saturn to do experiments with, especially learning about the lakes. That is a really exciting couple of experiments that some folks out at JPL and even some folks here at NASA Goddard are working on currently. There are lakes, there are liquid lakes on Titan. It's not water though, it is methane, which is really neat. Mercury, there's quite a bit of experimental work done, I believe at Stony Brook University up in New York, and then I believe somewhere in Europe. There's quite a few places in Europe that do planetary experiments as well. So Mercury, there's a lot of volcanic glass on Mercury. There's a lot of different kinds of metals on Mercury. We want to understand those kind of properties. There's salts and hydrates and ices on Ceres, the dwarf planet in the asteroid belt. So understanding how those salts would have erupted onto the surface, what kind of salt were we even dealing with? How would it have crystallized and evaporated, made this kind of pretty residue on some spots of Ceres? That is to be determined through experiments as well. Io, very, very tricky moon of Jupiter, but yes, there are plans, future plans to do experiments with high temperature, pretty high pressure experiments with Io type gooey, squishy lavas in that case. Also, another important thing with experiments too are called return sample missions. So we had the Hayabusa mission we had Hayabusa 1 and 2 actually take samples from various asteroids. We have OSIRIS-REx that had just visited Bennu as well, and it's currently en route back to Earth with a bunch of samples as well. So getting all these return samples, we experimentalists need to be ready to not only receive these return samples, but we need to be ready to go, what are we going to do with it? We just returned a bunch of samples from an asteroid. Cool, awesome. Now what? What are we going to do with it? So we got to plan ahead and get our instruments ready. Be very careful on how we're going to experimentally be careful with these return samples, though. But some really cool pictures from the OSIRIS-REx mission from there. So Faye had asked me to share a paper with everyone though on So I shared this particular paper, which is recent advancements and motivations of simulated Pluto experiments. Hooray! So it's supposed to be mainly a review of just, you know what, there's a lot of challenges with low temperature experiments, but we need this understanding of the materials in terms of their physics, their chemistry, and to enhance modeling. That's the main drive of all this. So whether you're wanting to do your surface, your interior, your atmosphere, in this case of Pluto, it really depends upon what instruments you want. What is your experimental setup? Do you want pure ice samples? Do you want mixtures of ices? If you're doing atmosphere studies, you're going to need irradiation lamps. So typically mercury lamps. Getting down to really cold temperatures, under 60K temperatures, you're no longer dealing with liquid nitrogen. You have to deal with liquid helium. This is very, very cold materials, hazardous materials. Different instruments, like I said, it all depends upon what you want to study. FTIR and Raman can give you your spectroscopy, the atomic molecular levels of your ice, but that's not going to really help you if you're doing atmospheres. So radiative measurements can also help. Scanning electron microscopy is really, really interesting. That's done, it's still a fairly new thing in planetary science, but it's really, really helpful. But it all comes down to experiments are hard. And definitely not for the faint of heart. So you have to do multiple samples. Not everything is going to work. You have to be able to reproduce your samples as well. You can't just do a one-time fluke and hope for the best. You got to do multiple samples. There could be technical failures, so understanding your equipment is very important. So yeah, it takes time, it takes cost, but there's a lot of benefit to it. It's a lot of fun to get through it. So I will send Faye these links to share with everyone later, though. But if you're interested in just reading more about what all has gone on with planetary experiments, what's the future of planetary science as well? So we had an experimental analysis of the outer solar system workshop quite a few years back. You can read those abstracts. The Planetary Decadal Survey white papers. So it's a huge collection of community white papers from people like me and the whole planetary science community coming together and go, this is what we want to study. Yay, this is really cool. If you're interested in doing an internship at NASA, there's that link as well. And then if you're interested in just, again, looking up paper abstracts, if you have to look up an abstract for, say, like a class, and Google Scholar isn't really giving you everything you need, or maybe you're just feeling stuck or something, I highly recommend this particular search engine. We just call it AdSabs, but it's the abstract search engine. So highly recommend using that as well through your undergrad years. Certainly helped me write a lot of reports, papers as well. But thank you all so much. Thank you, Faye, for having me here tonight, and happy to take any questions later. Thank you.
Thank you so much, Caitlin. It's like a virtual tour of the labs. Very impressive. All right, let's move on to our final speaker today, Shub. He's going to share with us his life story. Shub, are you there?
Hi. Can you hear me still? All right.
Yeah, go ahead.
Yeah, so Faye asked me to talk today mainly because, well, I just went through like the stuff we talked about, I guess. Like I applied to grad schools last year. Backtracking a little bit though. So my name is Shub. I'm originally from India. I came to the US to study my undergrad degree at Caltech. I graduated like 3 or 2 months ago in June with a degree in physics with minors in astrophysics and computer science. And I'm heading to graduate school to pursue my PhD in physics and astronomy at the University of Pennsylvania, which is starting in like a month, I guess. Wanted to talk a bit about like how my experience of being an international student at Caltech. because I think it might be relevant for some of our viewers. So when I was in India in high school, I looked at different programs available within the country and outside, and I found that if I want to study physics, like there are good options at both places, so I should try applying everywhere. And I went through the regular process of like taking your SATs, taking other examinations, filling out applications, applying to like a couple of different countries, like 5 to 10 places at every place, and then applying to places back home too. And by the end, like I was choosing between like an institute in every country, and I ended up going to Caltech because of its small size and the kind of research that like I could be exposed to. Caltech's great if you want to do astronomy and physics, which is what I wanted to do. Um, when I came to Caltech, I believe Sam last week also talked a bit about this, that Caltech is great to do research because we're really small and you get to like talk a lot to professors, connect uh, directly with them, which is what I sort of like ended up doing. It sort of happened organically. My freshman year, like my first year, I started working with the observational cosmology lab. And that extended into like a summer project, which extended into like next year's work, which extended into like next year's summer. So I worked with them for like 2 years, particularly doing CMB bolometer, working like directly and indirectly related to a CMB bolometer experiment that observes the cosmic microwave background from the South Pole, trying to look for signals from primordial gravitational waves. That got me really interested in instrumentation and how like you can build different things to do cosmology, which is what I'm going to be trying to be doing in grad school. This year, though, like I decided to like switch fields just to like check something else out. So I've been working in Caltech's Exoplanetary Technology lab, mainly doing direct imaging. Um, it's been a great experience at Caltech. The one takeaway like I have is like you need to like shoot your shots. Yeah, you need to like take all of the shots you can like get. Uh, like if you want to email a professor and you're scared that maybe they won't reply or maybe they won't care, you should still email the professor or you should apply to this random school because like that's what ended up happening for me too. Like there's no downside to sending that email or filling out that application or like asking for like a fellowship or something like that works some. Um, last year, like I started looking at graduate schools mainly because like my research experience at Caltech made me confident that I can bear grad school for 5 more years and I would enjoy doing research and I do want to like end up in academia if academia takes me after 5 years. Um, so I have applied to places that had like strong instrumentation programs. Ended up getting into a few like this last year has been like this last like 2 terms at Caltech were great because like all me and as well as like all of my friends were just like touring different graduate schools, just looking at all the cool research that's happening everywhere, and it's kind of amazing how little we know outside our field about all the cool things that other fields are doing. Um, so that was an amazing experience. I ended up choosing to go to UPenn because they have a great instrumentation program. I like really bonded with the advisor there, and they all like I also had another advisor I could work with at the same time on some data analysis project because I wanted to also simultaneously learn that. So at Penn, I would be working with like large scale surveys to do cosmology things, which I don't really understand yet. But on the instrumentation side, I'm working on a Lubin telescope that does line intensity mapping, which is supposed to fly in 3 years, so right in prime time for my graduate career. Um, other things like I wanted to mention that might be relevant to some people is like being an international student in the US is tough. Like not everything is geared towards your experience. If you're coming from somewhere else, like most people from where I came from, like I did have a community of people who were applying with me to to undergraduate schools as well as graduate schools who were international. But it's tough if you don't have that community, which also happens to a bunch of my friends. So yeah, like it's a tough process, and the easy way to get around it is to like reach out to other people, because most of us also got help and we just pass it down. There are other resources so that I would be like glad to talk about to you directly if you reach out to me, which you can. Like, I'm pretty sure like emails and everything are like up somewhere on some website. Other than that, yeah, like if you're considering or thinking about like astronomy as a field, like it's research is tough. It's heartbreaking. Sometimes like you'll be working on something for a month and it will not work out, and then your advisor will tell you, hey, let's try something else, and you'll just like leave the thing you were trying for a month. And that happens. And that's, I think, the main thing, that if you're curious enough and if you're fine with like leaving progress for something that might be better, um, then you'll be fine doing research. And if you're like just excited about solving problems, you'll be great. Yeah, that's most of the things I wanted to talk about. So thanks, Faye.
Thank you so much, Shub. Yeah, as Shub mentioned, we'll post his email address on piazza.com if you have any questions regarding grad school application. Being an international student in US, feel free to email Shub about it. Okay, before we end, let me thank all the speakers again. That was great, excellent session, thanks a lot. Let me remind everyone to check out additional resources, our GitHub page, or course website. Next week, we'll meet again on Monday, and we'll talk about model feeding using radial velocity method in Exoplanet as an example. And we will also start to work on our final project for the workshop together next week. All right, take care, everyone. See you next week.